our final days today, and Anna Fino is gonna give his talk. Thank you very much.
Okay, thank you very much. So this is the last lecture, and it will be about balance metrics and Hall-Strominger system. So in the first part, I will review a little bit what is now about balance metric with some open problem, and then in the second part, I will talk more about Hall-Strominger system, how the reason why it's interesting and what type of construction I know. So let's start with balance metrics. Let's start with the definition. So a balance metric on a complex manifold is an Hermitian metric. I will identify, for simplicity, the metric with the fundamental form. So it's Hermitian metric omega, which satisfy the complex dimension in n. So if we satisfy such that if we take the differential of n minus 1 times wedge, this is closed. So omega n minus 1 is this close, and that means that omega is co-closed, is the same things, and that means that essentially you have n minus 1 form, which is positive and close. Okay, we will consider the case n bigger than 3, because when n is 2, then automatically a matrix that satisfies this condition is scalar. Okay, so this is a generalization of Kähler condition in higher dimension. In the literature, there are some equivalent conditions for a metric to be balanced, or for a compact manifold to admit a balanced metric. For instance, there is a nice result by Duchamp that say that if you take a Hermitian metric, this is balanced if and only if is in terms of the Laplacian. So let's say the Laplacian related to D, the Laplacian related to the bar. So a metric is balanced if and only if the Laplacian related to del of f is equal to the Laplacian related to the bar of f, which is equal to 2 times the usual Laplacian. That's right. Here, equal to 2 times, let's say, the usual Laplacian with respect to D for any function f, is infinity smooth function on your M with value C. This is a nice result due to Duchamp. The original definition of balance metric is due to Michelson. And in fact, Michelson found a nice characterization of compact complex manifold admitting balance metric. That's another property that is famous, as it is in terms of currents this time. So we say that a compact complex manifold M admits complex dimension n, admits a balance metric if and only if M has no, so it's a characterization similar to the characterization that we saw for Kähler and pluriclose metric, has no, let's say, currents of degree 1, 1, which are components of a bundle. This is due to Michelson. So what we are saying that our T, so doesn't exist any current of type 1,1, which are component of a boundary. So T equal to ds plus d bar s bar. That's what we have. And we have not many obstruction to the existence of balance metric. One obstruction, I think the only one, no, is in terms of complex and manifold, and is the following. If you have a compact manifold which is balanced, cannot have compact complex submanifolds which are codimension 1, homologous 0. Okay, so this given obstruction, for instance, this obstruction apply to the Calabi-Ekman manifold. This Calabi-Ekman manifold were already considered in the talk by Michael and are essentially diffeomorphic to the product of two dimensional sphere. Let's call S2P plus 1, S2Q plus 1. And the complex structure is constructed in such way, the Calabi-Ekman complex structure is constructed in such way, the projection between this product to the product of the complex projective space, CPP times CPQ, is homomorphic. Okay? And then one can show that using this projection and that project on the product of this complex projective space on this scalar manifold, you can construct easily compact complex and manifold of codimension 1, which are homologous to 0. Okay, so this manifold cannot have balance metric. Another nice way to construct compact manifold with balance metric is using what are called modification in complex geometry. So let's see now the behavior under modification. This is essentially due to a result by Alessandrini and Massanelli. There are many references in the literature about works of Alessandrini and Massanelli about balance metric. And let's start with recall the definition of modification. So let's take two complex manifolds, M and N are complex manifolds, and modification between the two complex manifold F from M to N is a homomorphic map such that there exists a complex submanifold Y in N, so here of codimension bigger than equal than 2, and outside essentially Y, okay, we have a biholomorphy, and F from X, the complement of the preimage of Y in X to N, to the complement of Y in N is a biholomorphy. Holomorphism given by restriction. Okay, so outside Y you have essentially a biholomorphism, and what is nice here that there is a nice theorem due to Alessandrini and Bassanelli that show that if you have a modification in the sense that I wrote before, and the Mn are complex manifold, then M is balanced if and only if N is balanced. So the modification preserves the balance condition. That's nice, because that means that also bimeromorphism birational transformation preserves the balance condition. Of course, scalar manifolds are in particular balanced, okay? So that means that you apply a bimeromorphy to a scalar manifold, you get something which in general is not scalar, but is balanced, okay? And that's the way, so what we have, a nice consequence that we have, that every compact complex manifold, which is bimeromorphic to a compact scalar manifold, is balanced. And this allows to show, to consider two classes of manifold. One we already saw are the Moisson manifold. In the lecture, in the second lecture, we show that this manifold cannot admit, was the Misha-Verbitsky result. Moisson manifold cannot admit pluriclose metric, but now we know that admit balanced metric. And in terms of bimeromorphy, these are bimeromorphy. You can look at the condition, are defined in a way that the algebraic dimension is equal to the complex dimension, but one can see Moisson manifold also bimeromorphy to projecting manifold, okay? And in general, manifolds which are bimeromorphic to compact scalar manifold are what are in the class C, Fujiki class C. So we have Moisson manifold, which are balanced, but also the complex manifold in Fujiki class C, okay? These are bimeromorphic to compact scalar manifolds. I didn't mention in the second lecture, but also that for the Fujiki class is a result by Gürsey. It showed that the complex manifold in Fujiki class C cannot admit pluriclose matrix. So from here you can see some duality between, in some sense, some different property if you have balance, if you have pluriclose matrix. Another nice construction, general construction of balance metric, which is more related to Hall-Strominger system, is the construction of balance metric using Conifer transition. I will say a few words about that. So balance matrix and Conifer transition. We'll say a little bit more about that. Essentially, this Conifer transition, or let's say we'll see that is a sort of contraction plus smoothing. So it's the formation of complex structures. So the idea, this construction is due to a paper by Fu, Li, and Yao. And the idea is to construct non-scalar balance 3/4, so complex manifold, complex dimension free, via they construct via the so-called Clemens-Friedman construction. I will just roughly speaking how it works, this construction, and especially we'll give a nice example on of balance metric, which is non-Kähler. All the, let's say, the compact complex manifold that will come from this construction will be in general non-Kähler, okay? Will be non-Kähler, let's say, Calabi-Yau. That means that they have all the property of Calabi-Yau manifold, so that there is, the complex dimension is free, so you have a free zero holomorphic form, never vanish, okay? But the metric is non-Kähler. Okay, so the idea is the following. We start with a Kähler. So today I will distinguish Kähler Calabi-Yau, non-Kähler Calabi-Yau, but Kähler Calabi-Yau is just Calabi-Yau. With a Calabi-Yau manifold, Kähler sense, M, threefold, dimension, complex dimension free. And then we take an M with a collection of K mutually disjoint, smooth, rational curves. Let's call C1, CK. So we have essentially K copy of P1, okay, with the property that the normal bundle of this curve are isomorphic to a copy of OCP1 minus 1, direct sum OCP1 minus 1. This condition on normal bundle is just an algebraic condition that allow essentially to contract these curves, this copy of P1 to points. And this is what we'll do essentially. So contracting the K rational curves, we get, of course, we get something singular, right? Corresponding, corresponding to all these curves that you contract to a point, you get singular point, double singular point. So we get a singular Calabi-Yau fall. Let's call them 0. Here I mean non-Kähler in general, so the Kähler condition is not anymore preserved. With K ordinary double point singularity. And we call this point P1, Pk. So we start with something smooth. We consider K rational curves with the property that you can contract, and then you contract to this point. Okay, what happened to the new manifold that you get essentially away from, let's say, the singularity? What we have that M removing, let's say, the curve, the union of the curve is B holomorphic by construction to what? M0, when you remove the point P1, Pk, right? And the nice thing here by the contraction stuff and by the fact that we are taking rational curves, how looks a neighbor of every singular point, a neighborhood? Of Bj in M0 is essentially isomorphic to a neighbor of the region where in this locus, which is given by zeta 1 square plus zeta 2 square plus zeta 3 square plus zeta 4 power 4 equal to 0 in C4. This is what you have geometrically. And then this is a result by Friedman, Friedman, Tian, and Kawamata. If we have an extra condition on the curves, if the fundamental, let's say the fundamental class of Cz is rational, so it's an element in A2 MQ, satisfy the relation. We have this extra relation that the sum over J, then we take Mj, Cj is 0 with Nj, the combination is such a way that Nj is different from 0 for every J. Then one can deform essentially M0 to a family of complex manifold. So they show that there exists a family of complex manifold. This is a smoothing. Before we did the contraction, and now we are doing the smoothing. MT, let's call MT, parameterize over a disk. Let's call delta this disk in C. And this is, we have what in the literature, so we go from M to M0, and then we have this smoothing. I will say a few words more about this, the property of this deformation of M0, but essentially this is what is called the Conifer transition. Due to Clemens and Friedman. And what are the properties of this movie? Such that, okay, essentially for t different from 0, okay, the MT is smooth. So the first thing is that MT is a smooth Calabi-Yau, general non-Keller, free-fall for t different from 0, and the other things that for t small, we have a control of what is going on near 0. The local model for this moving is isomorphic to a neighborhood of 0. Okay, you modify the locus that we wrote before. Instead of considering 0, the equation was something of order 4 equal to 0. Instead of considering 0, you would put just t. So this is the same, zeta 1 square plus zeta 2 square plus zeta 3 square plus zeta 4 power 4 equal t in C4. And the central fiber, so for t, let's say equal to 0, is isomorphic, is essentially M0. that construction is quite nice because the first remark, this is true to Friedman. Friedman showed that the smooth empty satisfy the Dirichlet lemma. It's not easy in general to construct complex manifold which are not scalar and satisfy the Dirichlet lemma. Satisfy the Dirichlet lemma, but in general, they are non scalar. And then another things that Friedman showed is that if you take, remember, S3 cross S3 is a special type of Calabi-Ekman manifold, so it doesn't emit balance, right? But if you take the connected sum of S3 cross S3 with K bigger than equal than 2, then this is balanced. As always, let's say, first, Friedman showed that you have a complex structure in this way. In this way can be constructed a complex structure on this manifold in this way, a complex structure. And the idea how is constructed this complex structure, the idea is to contract enough, let's say, rational curves on M such that A2, the second cohomology of your manifold, is 0 for T different from 0. And then having A2 0, B2 0 allow to identify the space as a connective sum on S3 cross S3. And then that's a theorem by Fu and Yao, Fu, Li, and Yao. They show that for sufficient small t different from 0, MT is a balance metric. So in particular, the previous manifold has balance metric. Okay, so they show that for sufficient small t, the new smooth manifold MT has a balance metric. So in particular, let's say that the connected sum of S3 cross S3 with K bigger than 2 is balanced. It's still open to see if in general there is on S3 cross S3 complex structure which admit a compatible balance. That's completely open. So the case K equal to 1. We know the answer no just for the complex structure due to Calabi-Ekman. Okay, more example. Let's see more examples of balance manifolds. And one example we already saw, okay, was in the second lecture, and this is the twistor space. If we take the twistor space of 4 manifolds, this was compact anti-set dual, Riemannian 4 manifold. We review how is constructed the complex structure. The anti-set dual condition makes the complex structure that I review to be the almost complex structure to be integrable, okay? And this is as a balance metric, essentially the standard metric that you can construct on that using the splits in horizontal and vertical is balanced. And this was shown by Michelson in his paper about balance metric, and also by Godusha. Yes, done in this. But there are more simple examples in terms of Lie groups. Just take, if you take a unimodular complex Lie group, G, complex in the sense that J is bi-invariant. The complex structure J is bi-invariant. Okay, so that means they commute with facts. I will not write that, but it means that commute with a joint representation was shown by Abena and Grassi that any left invariant Hermitian metric on G is balanced. In fact, this is if you take a complex Lie group and a left invariant Hermitian metric is balanced on your Lie group if and only if the group is unimodular. And the proof is very simple. I was just say a few words about that because it's a nice computation and is very simple. So the idea of the proof is the following. Let's take the co-derivative of omega is a one form applied to x. This is a general formula. If you use the orthonormal frame, this is just a sum from I to 2n, or what? You take the Levi-Civita connection, ei omega ai x. This is the general formula that one has, and this is exactly equal, that's the computation, to the trace of add jx. So you can see from here that omega is co-closed if and only if the trace essentially of that jx is 0 for any x. That's why the unimodular case give you in a natural way balance metric, and this allows to construct also in a natural way the balance metric on what is known in the literature the compact complex parallelizable manifold. Okay, so every compact complex parallelizable manifold, which are essentially the compact quotient of a complex Lie group by lattice gamma, have balance metric. This is very simple to construct. And I want to mention a result by Yaku, is on his PhD thesis. He showed that in the case, this is very curious, if the complex Lie group G is semi-simple, then the omega n minus 1, we know that then a left invariant, okay, metric, omega is automatically balanced, it is more, and then omega n minus 1 is not only close, but is exact. That's curious. So it's not only close, but is an exact n minus 1 form. Here I mention also some results that I got with Grancharov and Bezzoni, where we study something more general than complex parallelizable. We found a characterization of compact, complex, homogeneous spaces with an invariant volume 4. That means that there is a complex structure and then a volume, okay, which is preserved by a Lie group by a transformationally group that are transitively on your manifold. That's more or less mean. And the nice thing is that we found out that C1, this characterization, C1 has to be different from 0. These are in general essentially torus bundle, or torus bundle, this manifold over the product of a complex parallelizable manifold that we considered before and generalized from manifold. Okay, we use such theory to have a characterization. What turns out that for such type of complex manifold, the existence of balance metric turn out to have something for C1 different from 0. And then there are some classification for more general Cobalt local homogeneous space. From, for instance, Gürsey classified in manifold of real dimension 6 with a balance metric. I got a classification with my student Paradiso in the almost abelian case, and so on. Good. We already see from some example some interplay with other type of Hermitian structure. So let's see now what is known or not known, interplay with other type of Hermitian matrix. Okay. This is a result by Alexandrov, Ivanov, and Popovici given a different proof more recently. If you ask to Hermitian metric omega to be on the same time balance plus pluriclose, so that means co-close plus DD bar close, then automatically this is scalar. Okay. And that's the proof is essentially not difficult. We gave a different proof, for instance, in the paper with Parton and Salomon. It's different, but essentially what one use, that's omega n minus 2, which d omega is 0. That's essentially what we use. And then if we call this phi, we use d bar, phi is 0. That's the key of the things. Of course, this makes sense for n bigger than equal than 3, right? Because for n equal to 2, the balance condition is already the killer condition. We conjecture with Bezzoni that we have evidence for many examples that every compact complex manifold admitting a balance. So we have a omega, which is balance, and another, let's say, omega tilde, which is a pluriclose metric is scalar. And the curious thing is still open. This conjecture is completely open. And of course, it makes sense again for n bigger than equal than 3. And we know that the conjecture is true more or less for all the known at the moment complex manifold. Is true, just very quickly, is true for, okay, the twistor space that we saw before. This is essentially by Verbitsky result, because we know that is balanced by Michelson, but by Verbitsky cannot admit any pluriclose metric. We know for the Fujiki class also. See, this is a result by Gürsey, because from today we know that since this is be meromorphic to a compact Kähler manifold admit a balance metric, by Gürsey showed that it cannot admit any pluriclose. We know also for the, let's say, the Li, Fu, Yao manifolds that we considered before using transition, conifold by conifold transition. Why we know that? Because you can use the Hilbert lemma essentially. These are non-Kähler, but they satisfy the Hilbert lemma. And then they show essentially that also in this case, you cannot have any pluriclose metric. We know, this is a paper with Bezzoni, for the all known example of Nil manifolds admitting pluriclose metric. Remember that is true in dimension 6, but it's still an open conjecture. So for two-step manifold, we know that's the conjecture. Yeah, I mean, if you have a balance with J, of course, invariant, coming from left invariant complex structure on the important group. Also for this case, we show that essentially you have only the torus if admits both a pluriclose metric and the balance metric. We know also for some special classes of submanifold, 6-dimensional submanifolds with holomorphically trivial canonical bundle. This I obtain a classification of that, of this manifold with Otal and Ugarte, and with Bezzoni we show that you cannot have both the condition and that unless you get Kähler. Another type of manifold is for almost abelian. This is in all dimension, in any dimension, almost abelian submanifolds. And this is a paper with Paradiso. And here it's curious because what we did, essentially, this is quite explicit. If you have a pluriclose metric and the balance metric, then using these two, you can construct a Kähler metric. So it's really constructing. And then we also, this OT manifold yesterday in the lecture by Alexandra, she mentioned the construction of OT manifolds, and she mentioned that they are not balanced. This is shown by Alexandra, Ottima. So also in this case, a more example, because recently there were other construction of balance metric and all the time. So probably yes, is general, the conjecture is true, but we don't know how to prove it. I want to mention a result that I got with Grancharov. And this is being with globally, in fact, conformally balanced condition. We will see this condition later for the Hall-Strominger system. And the theorem that we show is the following. If you take a compact Hermitian manifold, with holomorphically trivial canonical bundle. So in particular, C1 is 0. And plus, we ask that the Ricci of the bismuth is 0, right? Like the Calabi-Yau case, you have a Kähler-Ricci flat metric. Here you ask that the Ricci of the bismuth is 0. Then when we show that must be globally conformally balanced. That means that there is a function f such that if you, in the conformal change, if you take the conformal change, you have omega n minus 1 times this is 0. So conformal metric is balanced. And that's what's nice because allow us to construct a counterexample to a conjecture by Gürsey, Ivanov, and Papadopoulos. They conjecture that anytime you have a compact complex manifold with C1, 0, then it admits an Hermitian metric with holonomy of the bismuth connection containing SUN, very strict holonomy. And using these essentially things, we construct a counterexample because we construct a compact complex manifold which has C1, 0, but it doesn't admit any balanced metric. And then we could find a counterexample. And I have not, maybe I will skip the proof of this, but it's really using essentially the expression of the Chern form, the relation between the Chern form and the bismuth form, because what is using in general that essentially we have that we know that rho C is d j d of log determinant G alpha beta bar. Okay, this is our C, and essentially what was essentially to show that the condition that you have holomorphically trivial bundle, you have this N0 form, non-vanishing, which is holomorphic, and then you write like down this way locally. You can write down in this way with F holomorphic function. And then what was essentially a nice part was to show that rho C is essentially equal to minus dj d of log of the norm sigma square. One can write down everything like that. And so what essentially did is just a conformal change from omega to the norm of sigma square omega. This is the conformal change that we did at the end, and we showed that essentially if this is omega tilde, essentially to have this star of omega tilde d close is equivalent to have omega tilde d star close. That's a key, but that's the way how you get the conformal change. And one can ask with other type of Hermitian metric combined with balance. There is another type of metric in the literature that is called Asteno-Keller metric, was introduced by Yoss and Yao on complex for dimension n. And it's a condition that d bar of omega n minus 2 is 0. Of course, for n equal to 3, it's just a pluriclose condition. And if you combine the existence of a compact complex manifold of a balance plus Asteno, you don't get Keller. So this time, balance plus in the sense of existence, okay? Because if you have a metric which is balanced plus Asteno-Keller, then is again Keller. But if there is a balance plus exists Asteno-Keller on the same complex manifold, then automatically is not anymore 2 that is scalar. And in fact, we construct an example, a simply connected example with Granchero and Vezzoni. Of course, the complex dimension is bigger, is at least 4. And we construct, for instance, such example on SU5 or T2. And other examples are constructed by Ugarte and Villacampa, Adela La Torre, I think, on Neal manifold. Okay. Before to go to the Hall-Strominger system, I want to mention a problem in general. In the second lecture, I didn't write explicitly the expression for the pluriclosed flow, but there is a flow that preserves the pluriclosed condition. So you start with a pluriclosed metric, then you evolve the metric, the complex structure is fixed, and the pluriclosed condition is preserved. For balance metric, for the balance condition, it seems to be harder to find flows preserving, because pluriclosed flow is not the only flow preserving the pluriclosed condition. For instance, you can have also the Chern curvature flow is involving the Chern form and so on. So it's not the only one. For the balance condition, it seems to be harder to have a flow preserving that. And one type of flow, essentially there are 2 types of flow that at the moment are known to preserve the balance condition. But unfortunately, they don't preserve the pluriclosed condition. So of course, a natural problem would be also, can we have a flow evolving the balance condition and the pluriclosed condition? This is completely open. Okay, the balance flow was introduced by Bedulli and Vezzoni, and this is essentially a generalization of the Calabi flow. I will review a little bit about that. First, we define the flow, and not much is known about this flow. I studied with my student, with Fabio Paradiso, this flow on almost abelian Sol manifold, but there is no general result in general, unless the result by Bedulli and Vezzoni. So let's take a complex manifold with a balance metric omega 0. So we start with that. This flow was defined is a parabolic flow. Preserving the balance condition is the following. So the problem here, the main problem here, that when you consider something evolving the pluriclosed metric, you evolve the 114. Here, what you do is to evolve the n-1 form, right? Because this should be positive and the close. So that's what you evolve. So you evolve let's call phi t n-1, n-1 form, positive, and you evolve in this way. T bar star over the metric induced by phi t, and then you take the Chern form associated to omega t. Omega t is a 1-1 form associated to phi t, okay? Star wedge star t phi t, you have this part plus this other, which is just a Bochern Laplacian. I will not write the expression, but in the slide is Bochern Laplacian, and this is a 4-order operator, essentially, this Bochern Laplacian. And then, of course, you have the initial condition. Phi 0 is just star 0 omega 0. So it is omega 0 n-1 times wedge time n minus 1. Okay, that's what the Dulli and Bezzoni show is a short time existence. So we have a short time existence on compact manifold, a uniqueness. And uniqueness. Compact manifold. This is due to Bedolli and Bezzoni. And what one can show that if, first remark, I think where it comes the idea to consider this flow, if omega 0 is scalar, then the flow is essentially the Calabi flow. The Calabi flow, the previous expression, so you just have the first part. In the Keller case, this second things is vanishing, okay? So you have only this part, and this is equivalent to essentially say that you have d phi t or what of E d bar, the scalar curvature. One can write down scalar curvature associated to omega t, where of course omega t belong in omega 0. So you are in Keller manifold plus I, d bar u positive, which is in the class, the RAM class of omega 0, and the condition omega 0 equal to omega 0. This is just a scalar curvature. And one can write that, and the nice thing of the Calabi flow, that this is okay for order, geometric flow. And in fact, is a gradient flow of what is called the Calabi energy. Which is just given by the integral over m on the square on the scalar curvature. So that's makes, so they essentially Bedolli and Bezzoni generalize the Calabi flow in terms of balance, okay, metric, adding that term. And okay, the Calabi flow, there are many results, and in the case of balance flow, what we show with Paradiso, we study essentially with Fabio Paradiso this flow, Calabi flow, not Calabi, sorry, balance flow, of course. Balance flow on 6-dimensional balance Sold manifolds. And what it turned out that the solution are defined for any T positive. It would be nice to see if this is always the case, even for many, for the known in manifold, you have the same property. So it would be nice to see, at least in the homogeneous spaces, if you have this behavior always, so you can have some blow up and so on. Okay, now let's go with the Hall-Strominger system. The solution to the Hall-Strominger system, I will not have time to say these things, but essentially can be also viewed as stationary point of some flow, which is called anomaly flow, which was introduced by Picard and Funk. So are some sense of related to a flow, is a flow of conformally balanced condition, let's say. And the idea of the Hall-Strominger system, let's say a few words about physics. describe essentially the geometry of compactification. I will say a few words about compactification of a theoretic superstrings with torsion. We'll see in which sense to 4-dimensional Minkowski space-time. So what is a string, roughly speaking, a string compactification is a process. So we want to link in a 10-dimensional manifold to 4-dimensional physics. That's roughly speaking the idea. So locally, doing these links, it means that locally you write your 10 manifold, locally is a product of, let's say, Minkowski space. You can take a copy of R1 free, so you have a Lorentzian metric times M6. And essentially, the geometric object that you use is essentially, so you have a 10-dimensional Lorentzian metric. And this Lorentzian metric on this product can be either a product or a Warpy product. We'll see in a moment the difference. So we have this Lorentzian 10-dimensional manifold, which is this product. And then you have a gauge bundle, a holomorphic vector bundle E over M6, because from physics you can see that in fact M6 is a special type of complex manifold. We'll see in a moment. In fact, it is real dimension 6 and is a special type of SU-free structure. So the idea is to reduce all the equation required by superstring theory to the geometry. So we reduce all the physics, let's say, not all completely. Okay, we'll see why. But anyway, we reduce almost all the equation coming from superstring theory to the geometry of M6, and of course also to the gauge bundle E. Okay, and essentially when one reduces, one look what is in physics called the bosonic part. Okay, and what is the bosonic part is a Lorentzian metric. Then you have a gauge connection. So you have a Lorentzian metric of signature 1, 9. Then you have what is called the flux. What is called the free-form Frank field. Okay, and that is a free-form H. It's called H, and is essentially I over 2 of d bar minus d, the fundamental form of the metric that you have in M6. And this determines completely the type of geometry that you have on your 6 manifold. Then you have a gauge connection on your gauge bundle, that's called A, and the dilaton, which is a function that they denote by phi, and essentially is log of the norm of, you have omega is a non-vanishing free zero form on your M6. So on M6 you have an Hermitian metric plus your M6 a posteriori has to have holomorphically trivial canonical bundle, and then you choose a non-vanishing holomorphic free zero form. That's more or less the object. And the first case in the literature, before the generalization by Li and Yao, comes from candelas, Horowitz, Strominger, Witter is 95. And is the case when the flux is 0. So the flux free compactification. So H is 0 in this case. And the product, so we have M10, like R locally, times M6 with product match. And what they show that you can take the product metric, it just correspond to the tangent bundle of M6. And then what is turned out from physics, then M6 must be a Calabi-Yau free-fall with Keller Ricci flat metric. And this we know that is the solution to the Calabi conjecture, okay, found by Yau. So in this case, let's say that the Hall-Strominger system reduced to Calabi-Yau theorem, because it's just like that. In this case, by Yau theorem, you know that there is a Ricci flat Keller metric in the class of omega, okay, and everything. So that is quite known in that case. But in the case when the metric is not product metric, but is a warping metric, that's from the Hall-Strominger system is the more interesting case. And this is due to Hall independently. The same here, 86 and Strominger. They describe what type is the case when H is non-zero. So the compactification with flux. And then what implies that M6 has to be again a Calabi-Yau free fall, but non-Keller, in the sense that I wrote before. Okay, so the canonical bundle is of M6 is still trivial, but not necessarily Keller. Okay, so now let's formulate our system, the equation of the system. So we start with M, our M6, which is a compact complex manifold of computation free with holomorphically trivial canonical bundle. So we choose a nowhere vanishing free zero, holomorphic free zero four with a nowhere vanishing holomorphic free zero four. We call this C. And then we have the other object, which is the gauge bundle. So A is be a complex vector bundle over M with a Hermitian metric that we call big H along its fibers. And let's denote alpha prime a real number, just a constant. This is what we call, is also called the slope parameter. From physics point of view, alpha prime has to be positive, but in the mathematical literature, there are also results when alpha prime is also negative by Fong and co-authors. So the Hall-Strominger system is essentially involve an Hermitian metric omega on M, and is given by three equations. The first equation is what is called the Hermitian-Yang-Mills equation. So you have essentially, here we use the chain connection on E, on the Hermitian bundle E with the Hermitian structure H, but in principle you can use other unitary connection on that. But what you should have that, okay, here FH is just a two form with values in endomorphism of E, okay? And the condition is the 2, 0 part and the 0, 2 part is 0, okay? And then it remains only 1 part. If you do FH wedge omega square, this is 0. And this is the Hermitian-Yang-Mills condition essentially for our connection. And then we have a second equation that was not written in this form, but Li and Yao found out that it can be written in this form and give a nice link with conformally balanced condition. And it's essentially this. Okay, let's take, so omega himself is not balanced, but if you multiply omega square with the norm of your free zero form with respect to omega, this is 0. Okay, so that means that omega is globally conformally balanced. And then the third one, which is the more difficult because it's involving, essentially is similar to, let's say, a curvature condition on your balance metric or conformally balanced metric is the following: E d bar omega equal to, here there is a constant alpha prime over 4, and then you have nabla is just, in principle, is an Hermitian connection on M. Again, you can think the curvature as here as a two form with values in and T1 0M. So you have trace, this makes sense. Okay, the trace part is in the endomorphic part minus the trace of FH wedge FH. Okay, you have this, and this is what is called the Bianchi identity, or also called the anomaly equation. And that's a more hard. This is really the more hard equation. And this is in some sense a curvature condition on your conformally balanced metric. It's not hard to solve, of course, the first and the second, but it's very hard in general to solve the third one. And the first solution that were found in the literature non-killer solution are due to Fu and Yao, non-killer solution. And what they use, okay, for that is a class of toric fibration over K-free surfaces. And the construction that they use is due to Gürsey, Rokushkin, sorry, not Shkin. And what they did essentially if you have a natural, let's say, a balance metric that you can construct, I will say a few words in the last minute. But the idea is to do some ansatz on the metric using a function u, a scalar function. So you start with omega, which is balanced. We'll see in a moment how it's constructed, this omega. The torus fibrillation over Keller manifold, you can imagine what it is, but I will review a little bit. We talked already in second lecture, I think. The idea is to modify, to use an ansatz, to modify omega with a new omega u. And then the more difficult part is to write down the third equation in equation involving u. And the nice thing by Fu and Yao is to rewrite the equation in terms of a complex Monge-Ampère equation. And of course, the difficult part is to show that this complex Monge-Ampère equation has solution. There are also in the literature other non-Keller construction of solution for Hallström system I mentioned in the slides. I want just to the last minutes to explain how is the Goldstein-Pruching construction goes and how we generalize with Grancher and Bezzoni in the general case. So we start general case instead of considering K-free surfaces, we consider something with singularity, with mild singularity, like a K-free orbifold, but the solution that we get at the end was smooth, and we get also a new simply connected example of the solution for the Hallström system. So the idea is the following. Let's start with K-free surface with omega s, which is a Ricci flat Keller metric, and then we have omega big S, which is holomorphic 204. Okay, holomorphic 204 on S. Okay, what is going on? That was described by Goldstein and Pruching, that for any pair of omega 1, omega 2 of anti-set dual 1-1 forms on S, you need to construct the torus bundle. You need the topological condition that omega I up to the factor 1/2 pi is an integer class, given integer class. You need that. And then they associate, you can associate a toric vibration over S with, okay, if we denote theta, denote by theta I, the connection 1 forms on M such that you have the d theta I is the pullback under the projection of omega I. Essentially, omega I are the curvature to form or associated to theta I, and the complex structure that you have here makes Y to be holomorphic map. So that means that you have essentially the theta, which is theta 1 plus I theta 2, and this gives you the complex structure on the, and you have M as a natural free zero form, nowhere vanishing holomorphic free zero form, which is just given by theta wedge, the pullback of omega S, okay? And then you have also omega 0. If you take omega 0, given by the pullback, omega S plus I theta wedge theta bar, this is balanced. It's just a computation. One can check the d omega 0 wedge product, omega 0 is 0. And the Fuyao ansatz is essentially to consider, instead of omega u, okay? So you just, this is the same. So you don't modify this part, but you modify this part using a scalar function okay, like that. That's a tricky. So pull back over pi u exponential of u omega s plus the same theta wedge theta bar. Okay, so this part you don't change. And u is just a scalar function. And then the other part is to write down the whole Strominger system, the third equation, okay? And you write down essentially in two-dimensional complex motion pair equation with gradient terms, two-dimensional because you are on S. And of course, you will have this equation plus elasticity condition that ensures essentially that omega u is still positive. So I'll give you a Hermitian metric. And what we did with Granchanov and Vezzoni is to apply this type of, we remark this essentially, that we have a torus fibration, but in fact, what you have a foliated type of foliation, right? You have what is called a Calabi-Yau transverse foliation, okay, on your manifold. And since everything depends on this foliated structure, instead of considering S, K-free surfaces, we consider a type of K-free orbifold, okay? Of course, since you start with something which is orbifold, right? And you want, at the end, you want a torus bundle over that is smooth. But you start with something which is singular, like orbifold. So what we did is to use the theory of Seyfer S1 bundles. So first, we construct a Seyfer S1 bundle over our K-free orbifold, which was a particular one, but that can be done in general if you have mild singularity for your orbifold, which is smooth. So essentially what we need is a rational divisor by the theory of color. The theory of color allow her to identify this Seyfer S1 bundle in terms of the rational divisor essentially. So first we construct a smooth Seyfer as one bundle, and then the other, which is an ordinary as one bundle. And for that, you need essentially two rational divisor that satisfy special condition. And I think it's a good time to stop here. In the slides, there are more details, but I wanted just to give an idea of what is going on. So I think I will stop here. Thank you for your attention. I use all the time, sorry.
All right. Thank you very much. Any question? So thanks, Professor Fino, for all these great talks. It was a very nice opportunity for us and big energy from her. Thank you very much once again.
Yeah, I am sorry that I wanted to say more, but